This is the campus of the Bayerische Rundfunk in Munich-Freimann, and as shown before, these two buildings are the premises of the IRT. For mobile measurements, we use a well-equipped measurement car. While driving around the IRT, we are measuring the field strength every 5 centimeters. To get rid of fast fading effects, a post-processing calculates the median per distinct sectors. The field strength level per sector for some measurement routes is shown here. Now coming to the model, for every single field strength point, we are extracting data along a profile starting at the transmitter. These profile data contain distances versus heights, coverage codes and heights, and are supplemented by many more metadata like transmitter and receiver height, frequency, polarization, and many more. Here you can see one data collection corresponding to one field strength value. The goal now is, instead of measuring, to calculate the field strength based on these input data. For example, here is a visualization of one set of profile data beginning at the IRT transmitter on the left to the receiving point on the right. The model starts with calculating the line of sight and the first Fresnel zone. One submodel identifies buildings which mask this zone, and in this case that leads to a loss of around 16 dB. Another model only takes into account the most significant knife edge in front of the receiver, which leads to a loss of around 23 dB. The combination of many of such submodels lead to an overall prediction of the field strength level, which can be compared with an actual measurement. Model optimization means now to check how big these differences are and what dependencies can be deduced. Here the distribution of the difference between calculation and actual field strength value is shown over all profiles in decibels. The median difference is around 0, but there is a certain distribution around. For optimizing, we need to check dependencies like here error depending on profile length, on number of buildings that mask the first Fresnel zone, on distance to the house in front of the receiver, or per length of wood along the profile. The interesting part is the tendency of all errors shown in red and also outliers. So let's see why this point, for example, shows an underprediction of loss of around 13 dB, how the profile looks and how it was derived. The extracted profile shows a line of sight scenario and absolutely clear first Fresnel zone. But let's do a plausibility check. That is a picture where 3D terrain data of Google Earth are aligned by our topographic data. For example, with our data, we have obviously catched this little wood, the first buildings, that forest, we missed this one, but catch the next. We catch these 3 buildings, but the containers over here are apparently not stored in our database. Let's move on. And obviously there is a building in front of the receiver that has not been identified. And if we skip the 3D buildings of Google Earth, we clearly see that it does not occur in our data bank. Maybe it is a new one. So we would kick out this profile before a general conclusion of the model performance is done. With the help of many different error tendencies, empirical correction factors for the model can be deduced, and by optimizing step by step, a new mathematical model is born.